So in this second part of our tutorial, I will be covering the basic structure of a GA. The basic structure of a GA is as follows. We start with an initial population that may be generated at random or seeded by other heuristics. Select the parents from this population for mating. Apply the crossover and mutation operators on the parents to generate new offspring. And finally, these offspring replace the existing individuals in the population, and the process loops. In this way, genetic algorithms actually try to mimic the human evolution to some extent. Each of the following steps will be covered separately. So let's start with a generalized pseudocode for a GA that is explained in the following. One of the most important decisions to make while implementing a genetic algorithm is deciding the representation that we will use to represent our solutions. It has been observed that improper representation can lead to a poor performance of the GA. Therefore, choosing a proper representation, having a proper definition of the mappings between the phenotype and the genotype spaces is essential for the success of a GA. Here, I'm going to present some of the most commonly used representations for genetic algorithms. However, each representation is highly problem-specific, and you might also find another representation, or that another representation or mix of the representations might suit your problem better. The first, binary representation. This is one of the simplest and most widely used representations in GAs. In this type of representation, the genotype consists of bit strings. For some problems, when the solution space consists of Boolean decision variables, yes or no, the binary representation is natural. Take, for example, the 0 to 1 knapsack problem. If there are n items, we can represent a solution by a binary string of n elements, where the xth element tells whether the item x is picked 1 or not, 0. For other problems, specifically those dealing with numbers, we can represent the numbers with their binary representation. The problem with this kind of encoding is that different bits have different significance, and therefore mutation and crossover operators can have undesired consequences. This can be resolved to some extent by using gray coding, as a change in one bit does not have a massive effect on the solution. Real-valued representation. For problems where we want to define the genes using continuous rather than discrete variables, the real-valued representation is the most natural. The precision of these real values, or floating point numbers, is, however, limited to the computer. We have integer representation. For discrete valued genes, we cannot always limit the solution space to binary yes or no. For example, if we want to encode the 4 distances, north, south, east, and west, we can encode them as 0, 1, 2, 3. In such cases, integer representation is desirable. Permutation representation. In many problems, the solution is represented by an order of elements. In such cases, permutation representation is the most suited. A classic example of this representation is the traveling salesman problem. In this, the salesman has to take a tour of all the cities, visiting each city exactly once and come back to the starting city. The total distance of the tour has to be minimized. The solution to this TSP is naturally an ordering or a permutation of all the cities, and therefore using a permutation representation makes sense for this problem. Population is a subset of solutions in the current generation. It is also defined as a set of chromosomes. There are several things to be kept in mind when dealing with GA population. The first one is the diversity of the population should be maintained, otherwise it might lead to premature convergence. Secondly, the population size should not be kept very large, as it can cause a GA to slow down, while a smaller population might not be enough for a good mating pool. Therefore, an optimal population size needs to be decided by trial and error. The population is usually defined as a two-dimensional array of size population, size X, chromosome size. Population initialization. There are two primary methods to initialize a population in a GA. They are one, random initialization, so where you populate the initial population with completely random solution, or a heuristic initialization, where you populate the initial population using a known heuristic for the problem. It has been observed that the entire population should not be initialized using a heuristic, as it can result in the population having similar solutions and very little diversity. It has been experimentally observed as well that the random solutions are the ones to drive the population to optimality. Therefore, with heuristic initialization, we just seed the population with a couple of good solutions, filling up the rest with random solutions, rather than filling the entire population with heuristic-based solutions. It has also been observed that heuristic initialization in some cases only affects the initial fitness of the population, but in the end, it is the diversity of the solutions which lead to optimality. There are two population models widely in use. One is the steady state. In a steady state GA, we generate one or two offsprings in each iteration, and they replace one or two individuals from the population. A steady state GA is also known as incremental GA. Then we have the generational. In a generational model, we generate n offsprings, where n is the population size and the entire population is replaced by the new one at the end of the iteration. The fitness function, simply defined, is a function which takes a candidate solution to the problem as input and produces as output how fit or how good the solution is with respect to the problem in consideration. The calculation of a fitness value is done repeatedly in a GA, and therefore it should be sufficiently fast. A slow computation of the fitness value can adversely affect a GA and make it exceptionally slow, something which we really want to avoid. In most cases, the fitness function and the objective function are the same as the objective, is to either maximize or minimize the given objective function. However, for more complex problems with multiple objectives and constraints, an algorithm designer might choose to have a different fitness function. A fitness function should possess the following characteristics. 1, it should be sufficiently fast to compute, and 2, it must quantitatively measure how fit a given solution is or how fit individuals can be produced from the given solution. In some cases, calculating the fitness function directly might not be possible due to the inherent complexities of the problem at hand. In such cases, we do fitness approximation to suit our needs. The image that you will see shows the fitness calculation for a solution of the 0 to 1 knapsack. It is a simple fitness function which just sums the profit values of the items being picked, which have a 1. Scanning the elements from left to right till the knapsack is full. Now, parent selection. This is another process that selects parents which mate and recombine to create offspring for the next generation. Parent selection is very crucial to the convergence rate of the GA, as good parents drive individuals to a better and fitter solution. However, care should be taken to prevent one extremely fit solution from taking over the entire population in a few generations, as this leads to the solutions being close to one another in the solution space, thereby leading to a loss of diversity. Maintaining good diversity in the population is extremely crucial for the success of a GA. This taking up of the entire population by one extremely fit solution is known as premature convergence and is undesirable. The fitness proportionate selection is one of the most popular ways of parent selection. In this, every individual can become a parent with a probability which is proportional to its fitness. Therefore, fitter individuals have a higher chance of mating and propagating their features to the next generation. Therefore, this selection strategy applies a selection pressure to the more fit individuals in the population, evolving better individuals over time. Consider a wheel, a circular wheel. The wheel is divided into n pies, where N is the number of individuals in the population. Each individual gets a portion of the circle which is proportional to its fitness value. Two implementations of fitness proportionate selection are possible. In a roulette wheel selection, the circular wheel is divided as described. A fitness point is chosen on the wheel circumference as shown, and the wheel is rotated. The region of the wheel which comes in front of the fixed point is chosen as the parent. For the second parent, the same process is repeated. It is clear that a fitter individual has a greater pie on the wheel and therefore a greater chance of landing in front of the fixed point when the wheel is rotated. Therefore, the probability of choosing an individual depends directly on its fitness. Implementation-wise, we use the following steps. Calculate S, which is the sum of fitnesses. Generate a random number between 0 and S. Starting from the top of the population, keep adding the fitnesses to the partial sum P till P is less than S. The individual for which P exceeds S is the chosen individual. Now, stochastic universal sampling. Stochastic universal sampling is quite similar to roulette wheel selection. However, instead of having just one fixed point, we have multiple fixed points as shown in the following image. Therefore, all the parents are chosen in just one spin of the wheel. Also, such a setup encourages the highly fit individuals to be chosen at least once. It is to be noted that fitness proportionate selection methods don't work for cases where the fitness can take a negative value. Then we have the tournament selection. In a K-way tournament selection, we select K individuals from the population at random and select the best out of these to become a parent. The same process is repeated for selecting the next parent. Tournament selection is also extremely popular in literature as it can work with negative fitness values. Then we have rank selection. Rank selection also works with negative fitness values and is mostly used when the individuals in the population have very close fitness values. This happens usually at the end of the run. This leads to each individual having an almost equal share of the pie, like in the case of fitness proportionate selection as shown in this image. And hence, each individual, no matter how fit relative to each other, has an approximately same probability of getting selected as a parent. This in turn leads to a loss in the selection pressure towards fitter individual, making the GA to make poor parent selections in such situations. In this, we also remove the concept of a fitness value while selecting a parent. However, every individual in the population is ranked according to their fitness. The selection of the parents depends on the rank each individual has and not on the fitness. The higher ranked individuals are preferred over the lower ranked ones. Then we have random selection. In this strategy, we randomly select parents from the existing population. There is no selection pressure towards fitter individual and therefore this strategy is usually avoided. In the next tutorial, in the next part of this tutorial, we will be discussing some operators, including the crossover operator, and we shall be seeing how offspring are produced.